we are on to thermodynamics, and we can't really do much thermodynamics without talking about temperature. So temperature in a kinetic theory of gas type of way, which we'll get to, is a measure, or it's related to the average kinetic energy of particles. In a very functional way, temperature is what we're measuring with a thermometer. The three you'll see the most often are Fahrenheit, Celsius, and Kelvin. When we have a number in Fahrenheit, when we have a temperature in Fahrenheit, we might say 96 degrees Fahrenheit. That's how we'd write it. Celsius, we might say 21 degrees Celsius, and Kelvin doesn't get a degree sign, so it's just 275 Kelvin. These are not the same temperature as each other. Fahrenheit is a scale that's based on having a number range that fits for what we experience day in, day out. So 100 Fahrenheit is hot, 0 Fahrenheit is really cold, but that's about the temperature scale that we live in. Celsius is a scale that's based on water. When we have 0 degrees Celsius, we get water freezing. When we get 100 degrees Celsius, we have water boiling. So it's a very water-based scale. And then Kelvin is a lot like Celsius. The increments are the same, but the 0 is shifted so that 0 Kelvin is the absolute coldest we could get. We call it absolute 0. So I'm going to give you a couple of values, and we're going to see what these scales look like and how they line up. Okay, these are some numbers that we might be interested in. Water boils at 212 degrees Fahrenheit, at 100 degrees Celsius, or at 373, and it's really 373.15 Kelvin. Body temperature is at 98.6 degrees Fahrenheit. That is 37 degrees Celsius, and that's going to be 310.15 Kelvin. Room temperature. This is one that we do in Celsius first, really. 20 degrees Celsius, which is about 68 degrees Fahrenheit. You can make arguments about how warm or cold of a room that is, but 20 degrees Celsius is what we use for room temperature in a scientific setting, not necessarily what the room is set as. Water freezes. Celsius is the easy one to do here. 0 degrees Celsius, which is 32 degrees Fahrenheit. It is 273.15 Kelvin. Liquid nitrogen. Liquid nitrogen sits at a temperature of 77 Kelvin. That means that it gets a Celsius temperature of negative 196.15 degrees Celsius, and it gets a Fahrenheit temperature of negative 321. 0.07 degrees Fahrenheit. And then we've got absolute 0. Absolute 0 happens at 0 Kelvin, which is going to be negative 273.15 degrees Celsius, or if you like, negative 459.67 degrees Fahrenheit. Now, you don't need to know all of these numbers. There are a couple that are helpful to know. For a physics class, we're not really worried about Fahrenheit, but it's a good way of relating it back. So that one and that one. Those are particularly good to know. It's not a bad thing to know this, and I'll show you why in a second. For Kelvin, that one, it's a good thing to know one of those two. For Fahrenheit, there's not a whole lot that we measure in Fahrenheit in a physics class, so you don't really need to know them. But again, hopefully just a reference. So I want to give you how to convert from one to the other. To go from Kelvin into degrees Celsius, we're going to take a temperature in Kelvin. So let's go with 200 Kelvin. The way that we convert this is by subtracting 273.15. So we do this and we get negative 73.15 degrees Celsius, which means if we want to go from Celsius to Kelvin, we're adding that 273.15 back. To go from Celsius to Fahrenheit, we are going to do a couple of actions. We're going to take the temperature we've got, so let's say we start with 100 degrees Celsius. We're going to take the temperature we've got, degrees Celsius, times 9/5, and then we're going to add 32 to it. So 100 degrees Celsius times 9/5 plus 32 equals 100 times 9/5. 100 over 5 is 20, times 9 is 180, plus 32 is 212 degrees Fahrenheit. And then to go the other way, we're going to do 212, or we can go, 212 minus 32. We just have to do the order backwards. And then times 5/9 will give us our 100 degrees Celsius. Those are kind of the major conversions. I do want to show you kind of graphically what this looks like, or visually what this looks like. So the way that I think of this is like this. I have this line of values. And I might have, so these are Kelvin, these are degrees Celsius. So when I've got 0 degrees Celsius, that's 273.15 Kelvin. If I've got 20 degrees Celsius, that's 293.15 Kelvin. All I'm doing, these scales have the same difference between them. So an increase in 1 degree Celsius is an increase in 1 Kelvin. Like I said, very rarely in a science class would you use Fahrenheit, but here are some other things. In Celsius, a jump of 20 degrees Celsius, right? If I go from 20 degrees Celsius up to 40 degrees Celsius, that's a jump of 20 degrees. It's not getting twice as hot, but it's a jump of 20 degrees. If I convert these to Kelvin, this would be 293.15 Kelvin. This would be 20 degrees more, so 313.15 Kelvin. A jump of 20 degrees here is a jump of 20 Kelvin here. Now, if I had instead 40 Kelvin and 20 Kelvin, because 0 Kelvin is the coldest that we get, a jump of 20 Kelvin from 20 to 40 actually is doubling our temperature. The reason that we can't say that with Celsius is if we jump from negative 10 degrees Celsius to negative 20 degrees Celsius, we've multiplied by 2, but we're definitely not doubling our temperature. We've actually gotten colder. And it's just because that 0 point isn't at 0. However, a lot of the equations that we use in physics deal with temperature differences across a range. So one thing we'll do very soon is heat capacity, where we'll say like Q is mc delta T. This delta T is, strictly speaking, it's a temperature change in Kelvin, but a temperature change of 20 Kelvin is a temperature change of 20 degrees Celsius. So when we're doing a delta T, we can get away with either one. It works out just fine because that's just where the that's just kind of looking at the slope of our line, and the slope is the same.